chat today, I'd like to make the session as informal as I possibly can. So I've worked until very late last night. I've pulled together some slides and I tried to tailor my presentation to the context of Nigeria, to the context of Lagos, if you like. And if you have any questions as I move from slide to slide, then please just feel free to drop your questions in the chat box, and I'll do my very best to respond. Okay, so I'm hoping that this will be a two-way thing over the next 45, 50 minutes. Yeah, okay. Right, so I thought maybe just as an icebreaker, okay, and I won't take very long, only a few minutes, just as an icebreaker, okay? And to put things into context, I have a number of pictures of engineers, from across the ages, from hundreds of years ago until recent day, okay? And I'm going to name one or two of these engineers associated with the contribution into the field of energy, and see if anyone can recognize the picture, the faces of these names. Yeah. So the first one is Michael Faraday. So he was an English engineer who discovered the theory of electromagnetic induction. So the stuff that you've learned in science about how we can build transformers, how we can build electrical machines in order to generate electrical power and then to transfer this power over long distances. A lot of our technology nowadays is basically based upon the work that he did so many years ago. So the first name is Michael Faraday. So can somebody tell me the name of the pictures which is associated with Michael Faraday, please? Just very quickly then. Any takers? Derek Abuke has entered. Oh, sorry, yeah, this is just somebody else waiting to come in. I'm just wondering if I can see the chat box. No. Probably not. Well, anyway, the answer to that is number 8. Okay, so number 8 is Michael Faraday, and his contribution enabled us then basically then to build all these wonderful electrical machineries which allow us to move electrical power, electrical energy over long distances. The next one is James Watt. James Watt. Which number then is associated with the name James Watt? James Watt was a Scottish engineer who invented the world's first steam engine, okay? And his invention basically created the Industrial Revolution in the UK and then spread then across the world. No takers? So the answer to that is James Watt is number 3, okay? James Watt is number 3. And so these two names are associated with the development of inventions and theories, engineering knowledge, which are related to the usage of energy, basically. Yeah. So moving very quickly then to the topic of the talk today, if I can move my screen. Can I just check that you can still see my screen?
Yeah.
Yes, we can.
Thank you. Thank
yes,
you.
we can.
You. Excellent. So the smart grids distribution. So this is basically how the so in the very near future, hopefully in the next, I don't know, 15, 20 years, okay, in terms of the generation of electrical power and usage, this can be summarized in a cartoon looking like this. Yeah, can be summarized in a cartoon looking like this. So on the top, you see renewable energy sources. So things like electricity creation from hydroelectric, for example, electricity generation from wind, electricity generation from the sun using PV panels, combustion of biomass and not coal or fossil fuel in order to generate heat, and heat can be then converted into electrical power. So these are the new forms of electrical power generation which are coming into the supply chain, so to speak. Yeah? And it's very, very important that we try to increase the amount of renewable energy that we can introduce within the supply chain, so to speak. A lot of our energy nowadays still comes from the burning of fossil fuels, so burning coal, for example, burning of gas. I've had a look at the literature, and the power station closest to Lagos, okay, it's something called the Egbin Power Station, I believe, and they're located near Ijede, which is about 40 kilometers north of Lagos, if I'm not mistaken. And this is basically an example of the current technology that we have in terms of generating large amounts of electrical energy and then feeding that electrical energy to our clients, so to speak. So moving on to the future, then we're hoping to see a larger proportion of electrical energy being generated using other means, and so therefore we can reduce our reliance on fossil fuel. That hopefully then will burn less gas, will burn less coal, will burn less fossil fuel effectively then to generate the electrical energy that we need. Yeah? So into the future, then basically you've got all this energy coming into the system, So if you were to look at the cartoons inside the circle, yeah, the cartoons inside the circle, if I can just pull out my laser pointer. Okay, so if we were to look at the cartoons inside the circle here, so electrical power effectively is required by homes. So in the context of Nigeria, I guess air conditioning is key. Okay, it's required by small factories and industries demanding these energy. There's also a growing trend of people putting, for example, PV panels on their roofs, on their roofs, and I'm sure you can see such examples very commonly in Nigeria as well. So effectively, the users themselves will, to a certain extent, generate their own electrical power, electrical energy, effectively. So the balance of the supply and demand will become much more complex going forward. So our ability to measure what people need, our ability to look at what is currently being produced, and then matching that supply and demand will be key in the energy supply chain of the future. The expansive name for this future energy supply chain is called the smart distribution grids. Yeah. Okay. So if you were to look at the cartoon on the top left, okay. So the pylons here basically is represents the infrastructure which will allow us to move electrical power from the source point and distribute that to the users. And then we need to have a very clever way of managing the balance of supply and demand. And then in order to do that, it's important for us to have feasible energy storage options. So one popular one is pumped hydro. So for example, in the nighttime, when the demand for electrical power is less, we can actually use the power generated in order to move water from a lower elevation to a higher elevation, and then allowing that water to flow again, to run the turbine when there's a heavier demand on the following day during lunchtime or when people come back into their homes after work. Yeah. One key area of the energy distribution chain in the future is the electrification of transport. So one of the key developments now, and this is something which the university is involved in a very, very big way, is basically replacing the internal combustion engines within cars. Okay, so we're taking the engines out, the old engines out, engines which require, for example, things like petrol or diesel to run, and then replacing that with electrical motors effectively. Yeah? The idea is very simple. If we can take the power of the sun, okay, and then feed that clean electrical energy into the motors, then we'll have the ability to reduce the levels of air pollution, especially in congested cities, many congested cities around the world, okay, which will help to bring down air pollution and also reduce our carbon footprint, okay? So just to give you an idea of the overall pictures of where we would like to go to in the very near future in terms of the feeding of the energy into the supply chain, how it is managed, how it is used. Storage is a key aspect of smart grid technology. So supply, if the power isn't taken up by the users 100%, then where do you store this energy when there's a peak demand in the short term? Yeah? For some reason, I can't move my screen. I have to go back to the presentation slide. So if you can just bear with me for 2 seconds. Yeah? Okay, so just to put things into perspective before we move forward. Okay, so I've got basically a picture of a power station, a stationary power station. It is based in North Yorkshire. So if you were to look at the map on the right-hand side, okay, so Nottingham effectively is more or less the center of England. Okay, let me just pull out the pointer as well. Okay. And this particular power station is located roughly about 2 hours drive north of our park campus. It's roughly about here. Okay, roughly about here. It is called the Drax power station. Okay, so for those of you who are familiar with the units and numbers, so Drax power station is the largest power station operating within the United Kingdom. Okay. It runs currently on a mixture of coal, okay, coal and also biomass, okay, and it has the ability to produce about 3.9 gigawatt power of electrical energy. Yeah. So just to put things into perspective, the meaning of the number 3.9 gigawatt electric, basically, it produces enough electrical power to feed to about 2 million homes. Okay, so in terms of population, if you assume that there are 3 people in a house, more or less, so we're talking about roughly about 6 million people. So this particular site has the ability to produce electrical power for the needs of about 6 million people. So in Lagos, I believe within the inner city of Lagos, the population is roughly about 14 million, okay, 14 million. So this particular power station will be able to provide enough electrical power for about half of the population of inner Lagos. Yeah? Just to give you an idea of the size and capacity. Yeah? So once we have an idea of size and capacity, if you move on to what is currently happening, okay, and then comparing the cost of some of the renewable options. Yeah. So what I have here basically is a chart taken from an organization called the International Energy Agency, the IEA. Yeah, the IEA. The IEA effectively is an intergovernmental organization. They have an office space in Paris. And amongst their many functions, they also serve as an information source for information of any information related to energy, including renewable energy. Yeah, including renewable energy. So if you were to look at the information about installation cost of various renewable energy technologies, we're looking at 4 different colored lines, okay? And one of them is PV. The bright yellow is PV. Yeah? So if you were to look at this chart here, this line here basically represents the fall, the drop, okay, in the cost of PV technology, okay, over the last 10 years, over the last 10 years. So from 2021 all the way back to about 2010, about 10 years. Yeah? And you can see that it's a lot cheaper for us to actually buy PV panels and use PV panels to generate electricity as compared to the cost of the same technology about 10 years back. And one of the key reasons for that is because of mass manufacture. A lot of companies are actually producing low-cost PV panels, and a lot of these companies, manufacturing-based companies in China, they can produce very large quantities of these at a reasonable cost. Okay, and there's also ample demand for that supply as well, which is basically then resulted in the favorable cost option for this technology. So comparing to, for example, offshore wind compared to onshore wind, concentrated solar power, which is a slightly different technology, then PV at the moment by far is the cheapest renewable energy option in terms of installation cost. Okay. For those of you who wish to find a little bit more information about this, then you're welcome. If you type in International Energy Agency, renewable energy on Google, on Yahoo, then you can find all these information available to you. Okay. Right. So how much renewable energy are there in the world currently, and where are we going in the next 10 years? Yeah, in the next 10 years. So just to give you an idea, if you walk around, the streets of Lagos, and certainly in the UK as well, you can find small PV panels attached to the roof of residential homes. It's a very common sight, It's a very common sight, but the PV modules can be combined, and there's a growing trend of large companies, of countries, basically then generating their electrical power using this technology. One of the key drivers, I've said, is that it is a lot cheaper nowadays to actually, buy and install a solar power station as compared to, say, 10 years ago. Yeah. So the rising capacity, the rising capacity of solar energy itself, the rising capacity of solar energy the growth has been exponential over the last couple of years, So, and it's not just confined to the land. So the satellite image that you see on the top left, okay, on the top left, this one here, it is actually a satellite picture of a solar power farm, okay, a solar power station, they call it. They no longer call it solar power farm, but a solar power station based in India, And this one here is located in the state of Rajasthan, which is on the northwestern corner of India, bordering Pakistan. One of the key reasons is that there's ample sunshine throughout the year for that particular reason. And there's large areas of arid land, so land which is not suitable for cultivation of crops. And they're basically making use of that land to erect large areas, for PV panels. They're so big that you can actually see them from outer space. Yeah. In terms of capacity, so the collection of all the panels here that you see is enough to generate about half of the capacities of the Drax. Yeah. So if you remember, can I go back? Yeah. So the power station which I showed you just now, okay. So Drax, based in North Yorkshire, it's capable of about 4 gigawatt electricity. So this particular solar power station in India is capable of about half of that. So you see all the collections of solar panels here, okay. They can supply enough electrical energy to about 3 million people. Yeah, about 3 million people. So if you had 4 of these, then collectively they should be able to supply enough electrical power for the entire inner city of Lagos, effectively. Yeah. So just to put things into perspective, if you were to look at the size of PV solar power stations, 2 of the largest are located in India, and then 1 located in China. And we are talking about very large scale PV farms. They're not only confined to land-based installation, okay? In countries whereby land area is scarce, okay? You don't have much land, for example, then there's also options for you to put PV panels in the sea, in the lake, for example, in large hydroelectric dams, okay? And there's a growing tendency of people putting PV panels on the surface of the rivers, of the lakes, in order to make use of the electrical connection already available, which is associated with the hydroelectric dam. Yeah. So moving forward, then, if you were to look at what we have currently, this is the global picture. Yeah, the global picture. So currently, we have the equivalent of about 50 Draxes in terms of the solar PV capacity. Yeah. So the combined capacities of the solar PVs globally currently equates to about 40 large power stations. And the IEA predicts that this is going to grow to about 4 times the current size in the next 10 years. So there's a growing tendency of people generating electrical power using renewable energy, using this technology in particular. And in the next 10 years, this will grow to roughly about 20 Draxes. Yeah. So it's a tremendous growth. But according to the executive director of the International Energy Agency, this Dr. Fatih Birol, in his latest publication of World Energy Outlook 2020, he says that despite a record drop in global emission this year, okay, because of COVID, so our emissions actually drop, okay. He's saying that the world is far from doing enough to put them into a decisive decline in order to better manage our carbon footprint. So although the trend of the graph is looking very positive, you know, we're seeing a tremendous growth in the appetite in the market for the generation of clean electrical power using PV technology. We need more of this. We need more contribution, not only from PV, but also from the other renewable energy sources within the context of the smart grid technology, which enables us to look at, you know, the details, you know, supply and demand, and in order to balance that. Okay. So hopefully this will give you an idea of what is happening in one aspect of the renewable energy technologies, where we are currently and where we are heading towards in the next 10 years, according to the International Energy Agency. Okay. Let's see if I can move the slide. Yes. So a little bit about our contribution in terms of the energy front. So at the University of Nottingham, we have a number of very strong research groups operating within the university, and within the Faculty of Engineering, the champion team effectively is the propulsion centers. Yeah. And one of the key things which we're looking at basically then is to develop technologies which will enable the electrification of the transport sector to take place much quicker. Okay, so basically generating, for example, electric motors which are very, very efficient, which are very compact, and hopefully then can even be used for the aerospace sector in the very near future. Okay, so over the next couple of slides, I'm hoping to give you an idea of what we do in relation to this particular area. Okay. So I'm from the Faculty of Engineering. Specifically, I serve within the department of EEE, so that's Electrical and Electronic Engineering. We are one of the best departments within the UK, according to the Guardian League table over the last 3 years running. And we host one of the largest research centers in the world in relation to power electronics and machine control. So in layman terms, a lot of the research work that we do effectively can be directly related to the design, creation of efficient electric motors, efficient electric generators aimed at the transport industry. Okay. So just to give you an idea of some of the work that my colleagues do within this research group, if you were to look at the picture in the middle, okay, so the blob of steel which Michele and John are looking at, that is an electric generator. Yeah, it's an electric generator. So if you were to look at the two shafts sticking from the back end of the generator, so if you're able to turn that shaft, okay, up to a certain speed, then this blob of metal can give you up to about 4 megawatt of electrical power. So what does 4 megawatt of electrical power mean then? So 4 megawatt of electrical power is more than enough, okay, to run, to operate a modern day commuter train loaded with passengers, your luggages, your bikes, your pet dogs from London to Nottingham easily, twice over, yeah. And if you were to look at the size of the electric generators, it's not very big. It's probably in terms of volume, maybe about 2 large suitcases worth of volumes. But in terms of its ability to actually generate the amount of electrical energy that you need every second, for example, per unit time, it is tremendous. Yeah. So a significant part of the work that we do, it really is into the development of ultra compacts. So as you can imagine, for marine application, for aerospace application, you don't want a large, big, clumsy chunk of metal for the generation of electrical energy, but something which is slim, streamlined, that would save space and also saving weight. Yeah, and it's ultra efficient. Although it is 98% efficient, so what that means is that the energy coming in from the shaft, okay, this particular generator can actually convert 98% of the mechanical energy into electrical energy, which is tremendous because state-of-the-art electrical generators can probably give you just over 90%. Yeah, so this one can give you 98%. Yeah. However, we still have to deal with 2% losses of energy, and this energy is primarily lost in the form of heat. So there's not much sound. There's not much sound, but primarily primarily in the form of heat. And so those of you with a calculator, so 2% of 4,000 kilowatt, okay, 2% of 4,000 kilowatt, it's roughly about 80 kilowatts worth of heat. So there's still a tremendous amount of heat that we need to dissipate in order to keep the generator cool so that it can function properly, okay? We have our own electric superbike, which we designed, developed, and assembled in Park campus, and we've actually took the bike and raced the bike in the European circuits of man. Okay, this is basically circuits involving the racing of electric bikes and not IC engine bikes, not bikes running on petrol, for example. Yeah. And we did very well. We did very well from 2015 to 2018. We were the European champions 2 years running, 15 and 16s. And just to give you an idea of the size of the engine, the power of the engines, it is effectively more powerful than the engines that you can find in the Porsche, for example. In the modern day Porsche Cayman, for example, yeah, the Cayman will probably have an engine of about, I don't know, 270 kilowatt, but the internal combustion engine is a lot less efficient as compared to an electric engine. So this one here, although it's 200 kilowatt, okay, it can probably give you about at least 90% of that 200 kilowatt in order to give you the acceleration that you need. And then more recently, we're looking to transfer this technology. So we're looking to take out the electric propulsions, the power electronics, and fit that into an aircraft. So we're doing this work together with an organization called the Air Race E. Okay, and Airbus is one of the founding sponsors. Okay, of this initiative. We're looking to stage the world's first ever all electric airplane competition. The idea was to have the competition take place last year, but obviously because of the COVID situation, it has been postponed, and it's only a question of time before the competition actually takes place. Okay. And then just one final slide in terms of our research activities before I move on to the rest. We're also working with a British company called Hybrid Air Vehicles in terms of developing the electric propulsion for what is essentially a giant helium balloon. Okay, any fans of Indiana Jones here? Indiana Jones. When I was about your age, when Indiana Jones hit the cinema, it was a big hit. Films by Steven Spielberg, and in one of the scenes, basically, then there was this large Hindenberg Zeppelin airship, which the Germans designed during the World War II, and the Hindenburg basically is the largest airship which was ever built, and in terms of size, In terms of size, the Airlander is roughly about a third of the length of the largest Zeppelins. Okay, but in terms of capacity, its ability to carry weight, so this guy is roughly about maybe 100 meters long, give or take, yeah, 100 meters long, and at full thrust, okay, at full thrust, it is able to carry roughly about 7 to 8 tons of payload. So in terms of payload, it's roughly about 8,000 kilograms of stuff that you can actually pile into the cargo area, and then the airline effectively can move that from one place to another. Yeah. So unlike a hot air balloon which moves up and down, this one here is actually capable of controlled flight. Yeah? So those of you who are interested to know a bit more about the Airlander, you know, there's plenty of information on Google, on Yahoo for you to look at. Okay, so all the research facilities, you know, in terms of doing research work, technical work, the labs, computer suites, and they're all located on our main university campus called the Park Campus near the city of Nottingham. And so this is where we are in the engineering facilities, if you like. Yeah. So for those of you who know the campus, you must have seen the clock tower. So the clock tower basically faces the lake here. Okay, so if you're standing in front of the clock tower looking at the lake, then all the engineering facilities is roughly about 15-20 minutes walk then to your left. Okay. So within the faculty, we've got students from all over the world. So I ran enough space to put all the flags. I've got Nigerian flag there, I think. Ugandan, and therefore I put a globe here basically to represent the nationality of students that we have at the university. I believe, according to the last count, we have students from over 80 countries present within our international community. And then as a faculty, looking at the energy sector, for example, you can find basically courses across the full spectrum of engineering, going from aerospace engineering to architecture and built environment, to chemical, to civil, to electrical and electronics, and obviously then mechanical materials and manufacturing. And energy effectively is a key theme that runs across all of them, yeah, across all of them. Okay, our courses are all accredited by the Engineering Council of the United Kingdom. So for example, you know, somebody doing electrical engineering, the course will be accredited by the IET. Somebody who's following mechanical engineering, for example, will be accredited by the IMechE. And then through an international agreement called the Washington Accord, then our degrees, our undergraduate degrees, are also recognized in over 20 different countries around the planet as well. So what I have here basically is the Chinese equivalent of the Engineering Council in the UK. Right, I guess this is the end of my presentation. So just really a very short sort of a talk about, you know, energy future, the importance of the role of renewable energy. Okay, how do we balance the complex relationship between, you know, supply and demand chain of energies. Energy storage is a key part. Okay, electrification of transport is an important element of the jigsaw puzzle, if you like. And then going forward, then as an example, you know, solar PV, I think will have a very big role to play, because it is cheap to buy, to acquire. It is very modular, so you can put 1-2 panels on someone's roof, or you can assemble it to a size on a park which is over a few square kilometers to generate very large quantities of electrical power. It can be land-based, it can be water-based. So the options essentially are numerous. Yeah, the options are numerous. Okay, I guess at this stage, I could take any questions that the students may have. Let me see if I... So do I have any questions then?
Good afternoon, sir.
Hello.
Good afternoon.
Yes, good afternoon. Good afternoon.
Sorry, I have two questions.
Go on.
Yes. So the first one is about the solar panels.
Mm.
And then during the presentation, you mentioned how there are some that are placed on the ocean. So I wanted to
Yes.
ask, is there no tendency of damage? Like since it's on the ocean, you have different aquatic lives living there.
Yeah. Yeah.
So yes, is there like a protection for it or something?
Yeah, that's a very good question, Jennifer. And so just to put things into context, Singapore, for example, yeah, Singapore is one of the richest Southeast Asian nation within that region. They don't have a lot of land, yeah, and they need electrical energy. They need power. Okay, so what options do they have? At the moment, they are buying a large quantity of their electrical power from neighboring Malaysia. They generate some, but they need to be able to rely on their own ability to generate electrical energy. So a viable option, effectively, is to put PV panels into the sea. Okay, so I guess space constraint is one driving factor. Okay, so if you imagine a situation whereby you can actually put these panels in a secluded lagoons, I'm not saying in an open sea facing the Atlantic Ocean. Obviously, then in terms of the design of where you put these panels, they have to be protected from large waves, so to speak. You know. The second key reason, there are three primarily. So the second key reason is that solar panels, they don't like the heat. So what do I mean by that? So for example, if I have the same solar panel in the UK in the month of July, yeah, and say at 12 o'clock in the afternoon in the UK on a nice July day, temperature may be about 28 degrees C, 29 degrees C. So it's not that hot. Yeah? The solar panel will give you about 250 watt of electrical power for every meter square. Yeah, for every meter square. What do I mean by that? So, for example, if you were to come, what time is in Nigeria? It's 12:30. Yeah. So if you come out and the sun is shining, so the amount of electrical power which is actually coming down onto your country at the moment is roughly about 1,000 watt for every meter square. Yeah. The solar panel can convert roughly about 20 to 25% of that energy. Yeah? So if you were to use the same solar panel, okay, in the Middle East in July, where the daytime temperature can soar to about 47, 48, then the efficiencies of the cells will drop, and it will drop tremendously. It will drop to about 20, 25%. So you will lose your ability to generate electrical power. You will lose to about 25% of the ability to generate power if you had the solar panel operating in a much cooler environment. So the second reason why people would put solar PVs onto the surface of water is so that you can have water basically to cool these panels during the hot days in the summer. In China, for example, you can find floating PV panels on the reservoir of hydroelectric dams. Which will make sense because you don't expect to see waves and poor weathers in these reservoirs, and there's already electrical connections because the hydroelectric dam, the key purpose effectively is to generate electrical power. So in terms of connection and a subsequent distribution, the infrastructure is already there. So it makes sense on multiple fronts. South Korea, for example, they're developing what will be the largest floating PV power station in the world. And in terms of capacity, it's going to be even bigger than the Ekbin power station close to Ijede. Ijede is about 1.3 gigawatt electric. The one planned for South Korea is going to be about just over 2 gigawatt electric. So changes are happening. Japan, for example, after the Fukushima nuclear accident in 2011, they had to import large portions of their electrical power, and they are, if you were to look at the developments maybe about 6, 7, 8 years ago, Japan had one of the largest floating PV panels in the world. So effectively, they were the first ones, and but that has caught on then with the other countries. PVs, and people are looking into using PV more and more. From a business perspective, it makes a lot of sense, okay? Because you don't have to find your fuel, you don't have to dig your fuel, you don't have to transport your fuel. When I came to the UK to study 20 years ago, we were burning coal. Over 70% of the UK's electricity came from the burning of coal. And we were actually importing coals from South America, coals from Venezuela, coals from Colombia, for example, transporting these vast quantities of very dirty fuel across the bloody Atlantic. It doesn't make sense from an energy footprint perspective. And so this makes sense from a cost point of view. So if you're investing money to build a PV farm, there's no headache about your fuel supply. I hope that answers the question, Jennifer. I know it's a long-winded sort of answer, but hopefully you'll be happy with that. Any other question then, please?
So basically, what you're saying is that.
Yeah. Sorry, Jennifer, I lost you.
I was saying, so basically what you're saying is that if the temperature is too high, the cells in the solar panel don't function well as they are meant to.
That is absolutely correct. Because at the end of the day, the solar cells effectively is a semiconductor device. Yeah. So your computers, for example, if it's too hot, your television, if it's too hot, then they won't be happy. The same thing.
Okay.
Yeah. Any other question then, please?
Yeah, there is a question. I want to ask something.
Oliver, go on.
Yeah. I want to. Is there any consideration concerning the kind of air that comes out from the location of the solar panels? Because I believe if the air is salty, we have a very vast effect on the panels. So do you consider the production of the panels? Is there any treatment that's given to the panels to be able to keep them safe from the salty air that comes from the I know most times they are getting close to the water or the very high sea. So is there any consideration to that?
That's a very good question. I think because the most of the panels are either monocrystalline or polycrystalline silicon cells. So effectively, it's glass. It's glass, but processed in a way that it behaves like a semiconductor. Yeah? So the surface of the cell itself, as long as you keep it clean, as long as the light photons can hit the cells will do their work. Okay? The key challenge effectively is the electrical connections between the cells, because each dot effectively behaves like a small battery. Yeah. So you have to connect the batteries in certain ways in order to generate enough voltage across. So the mechanical analogy is enough pressure, and then in order for it to generate enough current flow, so that you have something coming out of the panel. And in those sort of an environment, obviously, then these connections, these electrical conductors will have to be protected from the harsh environment, as you rightly said. So the effect of corrosion, for example, you're talking about water. You're talking about water cooling these panels. You're talking about salty water cooling these panels. So a lot of careful consideration will need to be made in terms of protecting the semiconductors and its electrical connections, so to speak, from the harsh environment. That's a very good, very observant view. Yes, absolutely.
Thank you.
No problem. How many do we have in the group today? About 18, is it?
Yeah.
And are these kids doing maths and physics and potentially thinking about doing STEM related subjects?
Yes, I'm the lecturer. I'm the physics lecturer in regional college.
Okay. Very pleased to meet you.
Thank you very much. You're welcome.
I really like the the question from Jennifer. I guess to many people, when you see pictures of the PV panel sitting on a lake or on the surface of a sea, you're like, what are they doing? But in many instances, it really does make sense. Yeah, Singapore basically, it's one key example. Any other questions? I know that you guys will have to have other commitments in 3-4 minutes time. Maybe one last question then. No? Okay. So in that case, then, thank you all very much for your time today. It's been a pleasure speaking to you and meeting again with all contacts, you know, and I hope that, you know, I will have this opportunity again to speak to you in the very near future. Then, okay. Trying to get start share. Yeah, let's try that. Chat. Right. Hi, Emma. You okay?
Yes, thank you. Good afternoon, everyone. I couldn't join at the beginning. So my name's Emma and I support the student recruitment team and my academic colleagues, such as Dr. Alex Chong. So some of you might have spoken to me during the fair that was organized earlier on in the year. And if you have questions about Nottingham in general, like if you've got an application with Nottingham, you want to find out about accommodation and like that, then you can book an appointment and discuss some of those things with me directly as well. So yeah. So if you have any of those general questions, I don't think we have time for that today, but the counselling unit have my contact details, and if you want to book a one-to-one session with me, I have a link that I can provide where at a time that's convenient for you or you and your parents or whatever, then you can always follow up with me as well. So thank you to everyone who has applied. Thank you to all of you for joining the session. I think wherever you're headed next, it's always good to understand the trends that are going on. You might not be coming to do an engineering program at university, but you could find yourself one day working as the head of communications for an engineering firm, you know, and you'll remember something from today's presentation. So just let your curiosity be sparked, go away and read up more and understand the world around you as best you can. Mm-hmm. So I'm always learning new things. The panels on water, I read about that not too long ago, because I think I can't remember where it is, but there's some canals. There's a country that has a lot of canals, and so obviously with canals you don't have waves crashing and so on, you know, exactly. So the water is very stable. Yeah. So I read about that recently and how that's one of the largest PV floating farms in China actually sits in the Three Gorges Dam, okay, which is basically the dam which generates large quantities of hydroelectric power. So there's actually one there, which makes sense, I think. Yeah. Because it's a still kind of lake setting. It stays cool and things like that. Yeah. So all right. Wonderful. Okay. Okay then. Thank you, everybody. So thank you, everyone. Enjoy the rest of your day. Have a good afternoon. Bye.
Thank
you.
All
right.
Thank you so much, Dr. Alex Chong.
Okay.
Thank you.
You're welcome.
Thanks, everyone.
Oliver.
Yeah.
So are the classes happening remotely in Bridge House now, Bridge House College?
Yeah, we are still on. We are doing a kind of we are online. We are doing online, and then it's staggered physical lectures.
Physical lectures, okay. Yeah. And then in the physical lectures, then you have to space the students around them.
Yes. We are observing social distancing. Yes. Yeah.
And that's basically what we're looking to do this coming September, because school effectively starts in September, end of September. Yeah. So the large classes will have to be via Teams, but then the smaller tutorials and computer lessons and things like that, seminars, then we will break them into small groups of 20, 30, 40, but they're spread over a large space, you know.
Okay. Depending on the size of the class.
We have to adapt. Yeah, we have to adapt. Yeah. Okay then. Yeah, it was very nice meeting you. And is Jennifer one of your students or your daughter?
Yeah, it's my very good student. It's my student.
Yeah, I like the question. It makes a lot of sense. Wonderful. Yeah. So we're very nice meeting you. And
thank you very much.
Okay.
Thank you very much. Yeah. Bye. Bye.